so this is a talk on point cloud renderer that I made. So by a point cloud, I mean that it's rendering lots of screen space points, pixels. When they get close, just screen space rectangles rather than rendering polygons. Why am I making a point cloud renderer? Well, polygons are good at making stuff like this.
Hey Tom, do you want to move over there? Sorry.
Yeah, okay.
You've been away. Thing then.
Yeah. They're good at making stuff like this. You know, flat surfaces, lots of surfaces. But the real world isn't really very commonly like this. It's kind of more like this a lot of the time. Might not be able to see that well, but just really messy, fuzzy kind of natural scenes where there are very few actual surfaces you can see, and rendering individual polygons doesn't really help you much compared to rendering points. So it's for this sort of terrain that point cloud renderers seem to be most advantageous. And in this talk, I'm just going to go through 5 of the different technologies that I put into the demo. The first is, well, how do you make a data structure from point cloud renderer, or how did I? And I made it all with sphere trees. So you have an outer sphere, and then that outer sphere has some properties, overarching properties of what's inside it, like the average colour of what's inside it, for example. And then each sphere has got children spheres within it. Sphere trees are quite useful compared to polygons that just approximate the surface, right? The sphere tree can approximate points or lines, curves, surfaces, even volumes. To give you an example, I've got some geometry here, some point geometry, some line geometry, some surface geometry, and if you made a sphere tree to store this structure, you have a large sphere, and then you would have 3 child spheres, and then taking...
Go.
Okay, where were we? Yeah, sphere tree. So you can store this geometry using a single sphere tree where this big sphere is the root and it's got 3 children, and just looking at the point geometry on the left gives that sphere its own 3 children, so it's recursive. And with a curve you can approximate it to 1 degree, and then you can go further and approximate it again. And because it's a sphere tree, you can approximate it to whatever level of detail you want to go down to, depending on how much memory you've got for storing the sphere tree. And for surface, quite similarly to the curve, for a particular patch, you could have 4 child patches which store a small amount of the geometry, and in turn each child patch could store a smaller set, etc., etc. Okay, so there's your sphere tree. The next question is how do you actually render a sphere tree? And part of that is deciding which spheres to draw and which spheres are outside of your view. So if we look top down and imagine this triangle is a view crystal. So your eye is here in a plan view and you're looking upwards. Just to take an example, if this is your geometry, these sort of points and curves here, then we need a rendering algorithm, and this is how it works. You start with whatever the root of the sphere tree is, so you've got a big sphere here, and you look through each of the children in turn. So this might be a child, and this is a valid child to continue to iterate down on because it's inside the view custom. And same with this one, but not the third child. So we continue to iterate down with the ones which are inside the view custom. So in this case, we see these children inside it, and again, so all inside the custom, you can iterate down again, and you're getting a closer and closer approximation of the actual geometry with spheres. And at some point you stop, because usually you stop at the point that you've hit the size of an actual pixel in screen space. So let's say that that's the size of a pixel in screen space, so you stop there, and you continue on with the other sphere, which is this one here. And again, you approximate closer and closer, but because this particular curve is a lot closer to your eye, you have to go to a higher level of detail before you actually stop and render the colour of that particular sphere. Okay, so that's data structure that's being used. The next question, this is a bit of a tricky one, is how to do occlusion culling. It's not mandatory, but I put it in as a piece of technology. So occlusion culling means that if you're staring at a brick wall, you don't actually try and render all of the geometry that might be past the brick wall. There'll be an entire landscape behind it. Equally, if you've got a large hill, there could be lots of other hills and buildings behind that hill. Is there a way to actually not attempt to draw all of that information? It's quite a tricky problem in general to do, so this is how it's done for this demo. Firstly, you need to try and draw all of your spheres from front to back and closest to furthest. And you don't need to do it exactly, but just roughly. So, assuming the landscape, for every sphere it's got children, and in my demonstration it happens to have 4 children. Each sphere has got 4 children. Now, if you assume that the 4 children roughly fit into these 4 corners of the sphere, then you can split up your kind of view into 8 different octants. And if you're facing, if you're in this little octant, half a quadrant, then the front back order is going to be 3, 4, 1, 2. So that will draw the closest sphere first, the second closest, third closest, first. And then the idea is that because you've managed to get that order right, if you do exactly the same when you recurse down to the next level. So for example, when you go to the children of 3, you do the same thing. Then roughly speaking, you end up with an iteration which is front to back. And then different orders depending on where you are. The next component of doing occlusion culling is how to kind of sort of map Z buffer. So, you can't see that at all. Okay. Oh well. You have to use your imagination a bit here.
Have you got the images on your drive which shows source images?
Well, these are the source images. It's just that they're kind of, you can see them on the laptop, but not here. Okay, I'll try and explain it. It's a bit confusing, but you have a Z buffer for your view. So this is a view of a scene where you've got some mountains here. This is your highest resolution image, your highest resolution Z buffer of the scene. So you're storing the data based on how far it is away, right? Every time you modify a pixel at this highest resolution, if it changes, then you go to the next resolution down, which is half the resolution, and you update it if it's further away. And then that recurses down. Again, if you've actually changed this pixel, then you go to the next resolution down, and you update it if it's further away. All the way down, but most of the time, whenever you change a pixel, you'll only do a couple of recursions. And what you end up with is a high resolution Z buffer here, very low resolution Z buffer down this end. And you can then use these Z buffers for occlusion culling on larger levels. So because every pixel here is the the maximum distance that you can get for that size area, then anything which is behind that maximum distance you can include. So the last part of it, the last part of the occlusion culling is that you've now got to know when to do the occlusion. So because we're rendering in a kind of hierarchical way, so we're starting with one big sphere and we're breaking it down into smaller spheres as we iterate to decide which pixels to render. So as you're rendering these spheres, if you're at the point where you've got a sort of larger sphere, then you check that sphere against the lower resolution set buffer. So you've only got to check against a couple of pixels because it's low resolution. And if it's behind these pixels, then you can include it and you don't have to iterate through any of its children. Right? So that's the way that you can occlude entire mountains if your lowest level Z buffers are closer than the mountain. And if you've got a smaller sphere, then you've got to check it against one of the higher resolution Z buffers. Like that. The next bit of tech that I put into it was something that most games cheat on, but because it's a tech demo, I've got to try to work out, try and make it a bit less hacky. So there's a problem with rendering any kind of landscape, which is that you want to be able to see things that are half a metre away from you, but also see things which are, well, the sun's 150,000 million metres away, 150 million kilometres away. If it's night time, you've got to see stars while they're even further away. So how do you, if you're not going to hack it, and you want to put everything in the same sphere tree, then how on earth do you get things that are so far apart from each other, or scales that vary by such a huge amount, into the same data structure? Well, the quick answer is to use flows. You can still store the position of a sun. It's not going to be as accurate, but you can get to that kind of distance with a float and still have accuracy for the things that are half a metre away. But it's not actually a very good solution, because if you want it to be a space game and you want to be able to fly to the moon, you might want to have just as much precision on the moon as you've got on the Earth. Or even if you're not going to be flying anywhere, if you're not going to be flying to other planets, you're still going to want as much resolution to do all of your physics on one side of the Earth as on the other side of the Earth. So unless you want to limit the size of your map to something quite small, floats really don't cut it. Well, we could use doubles, but that doesn't really actually solve the problem, because it reduces the problem, but then it creates another problem, which is, well, things are slower. And you've still got this problem that it's varying precision. So if you make some physics, intricate physics that works close to the origin, it just might not work the same far away. So the solution that I put into this is don't use a single reference frame. So there's no such thing as world space in the demo that I showed you. Instead, you've got multiple reference frames, multiple spaces. Just to give you an example using planets, the demo does have a sun in it, and you can see the sun if you look at the sky. The sun's inside a reference frame, so all these planets are within the sun's reference frame, and that might use units of millions of kilometers. Right, and the Earth's got its own reference frame, and the Moon's got its own reference frame, and they may be using units of kilometers, so that anything relative, anything positioned on the Earth will be evaluated in kilometers. If we zoom in on the Earth, then you can keep on doing this, so you can have patches of the Earth which each have their own reference frame, and those are going to be in meters. And that's down to the kind of resolution that you can be doing physics. So each of those has got a position on the centre of the Earth in kilometres, because it's relative to the Earth's reference frame. But anything relative to this patch is in meters. And this has got it's got the advantage of not having the precision problems. It's also got the advantage that you can have your reference frame have wires always up wherever you are on the Earth. So that simplifies AI and any game code that you do. The only downside is that whenever anything moves, you can't just change the value. You need to have a function which checks it when it moves. Has it moved into a different reference frame? If so, you've got to swap it in the sphere tree to be in a different sphere. So this is all in the sphere tree, right? We've got a big sphere, which is the solar system. Inside that we've got a sun, and we've also got the Earth and the Moon, and then the Earth is a sphere, and inside that we've got these patches as children. Alright, the fourth bit of tech that I put in is collision detection. In the demo you saw some rocks bouncing around, bouncing off the terrain. And in general, the rocks, they're not convex, the terrain isn't a high field, so we're not making any assumptions about the limits of the geometry. We've basically got, if we want to do collision detection, then we've got two arbitrary bits of geometry, like these two arbitrary shapes here, A and B, and we need to work out how they collide with each other. And the job of collision detection is just to work out where and how deep the collisions are between two arbitrary objects. Because we're using a sphere tree, we can make use of it and kind of iterate it like this. Well, we've got two roots of these two spheres here, and we know that the two spheres are intersecting, so we need to go deeper. And B is the larger sphere, so let's split B up first, and it may split up into, for example, three smaller spheres. This one isn't colliding with A, so we can ignore that. This one is colliding with A, so now A is the larger sphere, so let's split up A into its child spheres. That's not colliding with this sphere here, nor's that, and nor's that. So actually B doesn't collide with anything. So we can now move back to our third one. And we've already calculated these positions. So again, we look through at these four spheres and we find out that this sphere here is colliding with that sphere there. Again, this is the largest sphere, so we split that up. And we find that this last small sphere is colliding with this sphere. This is the largest sphere now, so we split that up, etc., etc. And you go down to whatever level of detail you like. So that's kind of helpful because it means that perhaps rocks that are far away in the distance, you may want to go down to just go to a lower level of detail. Things that are close, use a lot higher detail. So that's how I did the collision detection. And the last bit of tech is a terrain. So in a way the terrain doesn't matter, right? Because this is a rendering engine. You can put whatever data into it you want. But I think the terrain is interesting in itself because every time I run it, it generates a new piece of terrain. I don't know how much you guys were aware of plasma fractals, but that's how a lot of terrain is done when it's randomly generated. And there's an algorithm called the diamond square algorithm. So I'll just go through how that works. So let's say this is a top-down image of the terrain. Then at a very basic level, what you're looking for is a height field. So you want mountains to have a large height for each sphere, and Lowe. So your problem is, how do you get all that detail in the mountains? And we want a recursive system, so you start off with very low detail mesh. Let's say that we've just seeded this with a few heights for each of these spheres, or each of these points. The algorithm then becomes, well, how do you generate a high detail mesh from this low detail mesh? So, fairly simple. Let's take the sort of center square here. We make a new point in the center here, which is just the average of the 4 points around it. And then you add an offset, which is proportional to the size of this square. So if the square was twice the size, we'd add a twice as big an offset. And the offset is random. It can be up, it can be down. And so here we've just got the average of these 4 plus a random offset up or down. Where do we go next? Well, we can do that for all these squares, this particular example. Next, well, we can do something quite similar. This particular point here, you can do the average of these 4, and then add a random offset, vertical offset, up or down, in proportion to the size of this square, which is slightly smaller than the previous time. And you can do that for all those. And then we've got a few edge cases here as well. So, well, a good way to do it is just take 2 points, average those 2 points, and then add an offset. So there we've got all the edge cases covered. And now we have a grid which is twice the resolution that we had before. So we've got twice the resolution, we just repeat the process, and then you get 4 times the resolution, etc., etc. You can make it as detailed as you like. So that gives you a height field, which is kind of halfway there. Feel free to ask questions if you're on there.
Why do they call that plasma fragment?
Because if you render instead of height fields, if you make it colours, and you use a colour palette, just some sort of random colour palette, then it kind of looks like plasma. But if it's a height field, it looks like mountains. It just looks like this sort of strange plasma shape, colour shape.
So do you see the seed instead of the beginning of the original points? That's just the generalised, this side to be low and this side to be as high, or is that what you do?
Yeah, in my example I had 4 by 4 that you could randomly generate. Or you don't have to randomly generate it, whatever, if you wanted a big mountain to be somewhere. But you could start with just a 2 by 2, so you've got less data to start with. And it starts from a single random seed each time. And often, if it's a 2 by 2, then you just pick more at a height of 0 and work from there. So the next thing you do is you've got a height field, you colour based on height. This is like a really cheap trick for making it look a bit like terrain. If it's really low, make it blue like it's the ocean. If it's really high, it's white like snow. If it's in the middle, it's green like trees. Works quite well. And then you add a simple directional light. You've got a height field, you can work out the normal for each point. And after you've done that, you get something a bit like this. Now that's not from my game, that's just I got that from the internet, because lots of people do it. And you can see he's done white near the top and a bit of yellow near the water surface to make it look like a bit of beach. So that's a really simple, very standard way to make just mountainous terrain randomly. I added a few extra features to it. Firstly, once you get to the sand, just squash the whole thing vertically, and it means that your mountains come down and then you get sort of beaches. It becomes a lot flatter. Just kind of looks a bit more realistic. And then the last thing that I added was ambient occlusion. Because you're generating it on the fly, because you're generating it beforehand, you can add in your own ambient occlusion, just bake it into the mesh. And by that I mean, it looks a lot nicer. You've got mountains where all the hollows are darker and all the peaks are lighter. Because a simple directional light doesn't do that. It looks quite artificial.
So do you generate the mesh offline? And then
No, I generate it
Or-
as it runs, as it loads. So ambient occlusion is quite easy to do. You follow pretty much the same algorithm, but instead of each time that you generate a new point, go back. Every time you generate a new point, what you're trying to do with ambient occlusion is shade it based on whether it's really concave or whether it's really convex. So if you've got a height field here, you've done the average of the four around it, and then you've decided to either go up or down compared to the average. If you go down a lot, you want it to be a lot darker. If you go up a lot, you want it to be a lot lighter. And you have to average the shades of the ones around it as well. And just to give you an example, now this is the scenery in my demo, but without any directional lights and without any colouring on the terrain. And as you can see, there's a sort of hollow here, which is darker, and then the kind of little peaks of the rocks are lighter. And when you add in directional light on top of that, it just looks a lot more 3D than otherwise. And yeah, that's the end of my talk. If there's any questions, feel free to ask.
I have one. Before, when you were talking about the patches on the planet, how do you handle the seams between the patches?
Oh, the seams.
Yeah, so between those two kind of things there.
I'm not getting a contract.
Yeah?
Not getting a contract. That's the problem.
Yeah.
So there's no issues going, like, just rendering between the frames of reference?
No, not really. Not any more than just when you break up a single surface into its component spheres. It's the same thing as long as you've made sure that they fit together.
So we do the same thing for the Earth, but because they're polygons, you always the two neighbouring things when you always try to get gravity using a translation to move them. And if you use the edges and you're going to see, you can point that one issue.
No. You tend to get quite a lot of overlap on the individual sort of blocks, screen-based blocks anyway.
Mm-hmm.
How do you handle your Z with that? Like, you're saying that your Z blob space, you don't have the plastics going to Z
Yeah. So that's, well, it's a bit of a problem, but it's also not a problem. If you just use the floating point set buffer, then it's okay. Like you might think, well, you're losing precision at the distance again, but you're not really, because you're only losing it for the rendering. And because in the distance you're rendering bigger things, it doesn't matter, you've got less precision. So if you just use a floating point set buffer, that would work just fine. Well, this is a software rendering, so you could. It turns out that I'm not using a floating point set buffer because I'm doing it in 2 passes, sort of thing, which is an extra bit of tech that didn't really work too well. But I think these days you can do floating point set buffer.
Do you want to put the video on again so I can capture it on the
Yeah.
video?
Reference point for when we still have a workspace to be rendering. Everything still, we just use doubles rather than separate reference frames. And, doubles are pretty the same. We're going to try and do the sum of it, we'll just do the Earth, just for the Earth purposes.
Yeah. Yeah.
We still have a reference space to render.
Yeah, this was not really a practical thing, it's more of a conceptually how, if if you were going to have some sort of unbounded gaming world, what would be a good way to do it?
I guess it's just an arbitrary decision of how fine-grained that frame of reference goes down to the different frames of reference or so.
Yeah, I mean, you could do it on every single sphere. Every single sphere's got a frame of reference that its children are relative to, but then you have a lot of matrix transforms when you're iterating the thing.
Look at your data and look at the position lines. You get about 50 kilometers with close. If you want to go and say that this thing, you wouldn't get that much.
And at the point that you hit meters, you kind of want to stay in meters because all physics is good in meters.
If you doubles, you can pretty much say meters for the entire Earth and get a little bit accuracy to the millimeters.
Yeah.
But doubles will do the entire Earth just some millimeter accuracy quite well.
Yeah.
Not too good if you want to get another GPU accuracy, something like that.
But the problem is that if you've got an entire Earth and you're in Australia and your clock works, does the clock work in the UK? Because you've got less accuracy, even though you've got a lot more accuracy than a float, you've got less accuracy than when you're close to the origin.
Yeah, that was just insane. At that distance, it's not much for that one.
Make it full screen.
That's why we probably do physics on both sides of the different lines. Not that you would be running physics on both sides of the different lines.
No, but you might go to the other side of the Earth and be doing physics.
I think you would find it with like doubles. Yeah, I wouldn't go to the sun with it. Millimeter accuracy.
Mm.
Do the entire Earth.
Well, it might work, but
It's close that blows it all up. Close only close to 50 kilometers. 54 accuracy.
yeah. But it's also slower. Yeah. I mean, if you change your entire physics system to using doubles everywhere, you should be trying to do stuff in light space.
It's mainly the memory that goes up. It's just kind of making sure that everything actually sells in the unit. Before performance stuff these days, I was just it's hard to fix on what's up with forcing some of the CPUs.
Yeah.
I think doubles and angles know when you can get double memory, so it's
Yeah.
Vision system, I want to steal that vision system. That was good.
Yeah, there's